Hello and welcome back to Summer Work Help for Calculus 1. In this video, we're going to be taking a look at question number 13. So 13, the directions just say simplify slash rationalize. Okay, so for 13a, so for 13a, we have a fraction, which is equivalent to a quotient, right, which is division, right? So a fraction is just another way of representing a division problem, essentially, right? So for a, we've got root 20 over root 12. And because there's no number in the top left, these are square roots, right? So the square root of 20 over the square root of 12. So there's two. Notice the directions say it says simplify slash rationalize, and maybe the rationalize is redundant, but I wanted to kind of emphasize that there's two things we got to do in this problem. Is one, we need to, like, at the end of the day, we need to make sure that any square roots that are left in the problem are simplified. All right, so we've now, the past couple of questions, 11 and 12, and before that as well, we've been simplifying square roots, and that's still going to be true, right? So any square roots that are still in the problem at the end of the day have to be fully simplified. And it says rationalize. It is a mathematical convention, okay, that we generally don't want any roots in our denominator, okay? It's okay to have them in the numerator, but in general, we don't want any roots to be in our denominator, so we're going to have to fix that, all right? So there's a couple ways that you could start this problem. The way that I'm going to start is I notice that with both root 20 and root 12, both of them can be simplified, like on their own, right? Regardless of the fact that, like, they're in a fraction and one's in the denominator, one's in the numerator, but both root 20 and root 12 can be simplified. So I'm actually going to do that first. There are other ways of starting this problem, but this is how I'm going to do it, all right? So root 20, if I want to simplify that, all right, if I want to simplify the square root of 20, if I can simplify it, it means that there is a square number other than 1 that divides evenly into it, all right? Now, if that's not true, if there is no square number larger than 1 that divides into it, then you can't simplify it, and you just move on with your life, all right? But 20 does have a square number that goes evenly into it. If you don't yet know what it is, pause the video, see, can you identify? And same thing for the 12, right? So for both of them, there's a square number that goes into 20. There's a square number that goes into 12. So see if you can identify what that is. Okay. Hopefully, at this point, you were able to determine that 4, which is a square number because it's 2 squared, goes into 20. Right? It's the only other square number besides 1 that's going to work. All right. So we're going to rewrite 20 as 4 times 5. Okay. 5 is what's left over when you divide that 4 into 20. Right. So 20 divided by 4 is 5, which means that 4 times 5 is 20. And then on the bottom, the largest square number that goes into 12 is also 4. Right. So a little bit of a coincidence, but that's fine. Sometimes it's the same number. And because 12 divided by 4 is 3, it means that 4 times 3 is 12. Okay. So in the numerator, I can bring the 4 out. So the square root of 4 is 2. And then the root 5 is going to hang out for a second. And then also in the denominator, I pull out the 4 and I get 2 root 3. And my 2's cancel. So what I have right now is I have root 5 over root 3. I'm going to write it again down here because we got plenty of space. Okay. So we have root 5 over root 3. Now that is more or less simplified, except I still have a root 3 in the denominator, right? And I want to rationalize that. I don't want my denominator to be a root, okay? So the way that we, quote, fix that, the way that we get rid of the root in the denominator is I'm going to do a little trick that comes up in mathematics from time to time. This is a handy trick to have like in your pocket, okay? So what we're about to go over, it's not like earth-shattering, right? But it is a handy thing that can get you out of a jam in mathematics. You know, when you're in a situation like this, where like, I don't want this. How do I fix this? Okay, and what we're going to do is we're going to multiply by the number 1. All right. Now, we're allowed to do that, right? So it's like, well, first of all, like, are we allowed to do that? And then why are we doing it? We are allowed to do that because when you multiply by the number 1, you don't change anything, right? 7 times 1 is 7. -5 times 1 is -5. A billion times 1 is a billion, right? So when you multiply by the number 1, you're actually not changing the value. So there's nothing preventing us from just multiplying by the number 1. Now, the way that I've currently written it would not accomplish anything, right? So now we're getting to the why are we doing this, right? So if I just multiply by 1 like this, the way I've written it, well, that's not going to help us at all, right? So we are going to multiply by 1, but I'm not going to write 1 like that because that doesn't get us anywhere. Instead, we're going to multiply by the number 1, but I'm going to write the number 1 in kind of a weird way. I'm going to write the number 1 by root 3, because that's the thing that's in the denominator, okay, over, and then I'm going to put another root 3 in the numerator. So everyone should just sort of take a second and realize that this is 1, okay? So we're still multiplying by 1, which we're allowed to do because we're not changing the value at all. But I'm writing the number 1 as root 3 over root 3 because here's what's going to happen. When you multiply fractions, you just multiply across. And I'm actually going to start with the denominator because that's going to explain why we're doing what we're doing. The denominator is going to be root 3 times root 3. Well, root 3 times root 3 is root 3 squared. It's, I'll do it over here. So root 3, we saw this way back in question 1. Root 3 times root 3 is root 3 squared. Well, squared and square roots undo each other, which means I'm going to be left with just 3. So root 3 times root 3 is 3. And oh, look at that. I no longer have a root in my denominator, which is what I want. I want to rationalize my expression, all right? Now, obviously, I'm not done because I have the numerator. The numerator is root 5 times root 3. And when you multiply roots like this, you just multiply whatever's underneath the root, and that's your answer. So I've got root 5 times 3, which is 15. I have a root in my numerator, and I don't care. Okay? It is fine to have a root in your denominator, or sorry, in your numerator, right? And we rationalize this expression specifically to get the root out of the denominator. Also, the square root of 15 can't be simplified. Okay, so I did that kind of quickly, but I just want to emphasize that the reason why we're done is because root 15, there is no square number other than 1 that goes into 15. Okay, it's just 3, 5, and 15. So none of them are square numbers. So that's why we're done, because you can't simplify root 15, and the denominator has no roots in it. So that's our final answer: root 15 over 3. All right, 13b. We've got 2 plus the square root of 8 over the square root of 128. And I want to simplify / rationalize this. So for this problem, kind of similar to A, I could either start by simplifying the square roots, then rationalizing, or I could rationalize first, then simplify. I am pretty sure that our job is going to be easier if we simplify the square roots first, especially because the denominator is a relatively large square root that can be simplified a lot. So I think it's going to just make our job easier if we simplify first, then rationalize, and then if we have to simplify again, then so be it. So let's just go ahead and simplify root 8 and root 128 because both of them can be simplified. So I'm going to start with my numerator. So numerator, 2 plus, get the square root of 8. So I want to ask myself, what is the largest square number that goes evenly into 8? Well, my options are kind of limited here, right? Because 9 is larger than 8, so 9's not going to work. And so the only square number below 9 that's not 1 is 4. And 4 does go into 8, right? So this becomes the root 4 times 2, okay? I'll do it over here. Root, so this is root 8 is root 4 times 2, okay? And then when you pull the 4 out, you get 2 root 2. Okay, so I'm just gonna kind of jump right to 2 root 2. Okay, so the square root of 8 simplifies to 2 root 2. Then I've got the square root of 128. Same general concept. I want to ask myself, all right, what is the largest square number that goes evenly into 128? It was an earlier problem where I think I realized kind of an easier way to do this process. You can find this. One way of finding this is to start with the largest square number that's less than or equal to 128. Okay, because anything above 128 does not go into 128. Okay, so you can start by examining the largest square number below 128. Okay, well that's 121 because 11 squared is 121. But 121 is nowhere close to going into 128. Okay, so 121 doesn't work. Below that would be 10 squared, which is 100. Well, 100 also doesn't go into 128. Below that would be 9 squared, which is 81, which does not go into 128. Below that is 8 squared, which is 64. Now 64 does go into 128, so you can stop there. All right. There are other square numbers like 4 that go into 128, but 64 is the largest one, so that's the one that I want. All right. So what I have here is I have root 128. Again, I'll just do this as a kind of a sidebar. So I can rewrite that as 64 times 2, and when I pull the 64 out, I end up getting 8 root 2. All right, so the denominator simplifies to 8 root 2. Okay, equals. So I can still simplify this, and I'm also going to have to deal with the root 2 in the denominator at some point. We may as well simplify, I guess, first. So when I look at this, where we're at with this problem right now, I'm noticing that the numerator is a binomial, right? It's 2 plus 2 root 2, so there's 2 terms. The denominator is a monomial, 8 root 2, and all 3 of them have a common factor of 2, okay? So what I mean by that is this term has a factor of 2. It is 2, so it has a factor of 2. This term has a factor of 2 because it's right there in the front. And then this has a factor of 2 because 8 has a factor of 2. Okay? So all 3 terms have a factor of 2 in them. So what that means is I can divide out a 2 from all of them. Okay? And if you don't see that, all right, if you don't see that all 3 terms have a factor of 2, as a sort of an intermediate step, this next step is not really, quote, necessary, but it might just kind of help you see it. If you factor out a 2 from the numerator, you're left with 1 plus root 2, and then the denominator is, the 8 you can rewrite as 2 times 4, all right? And now you can see that the 2's are going to cancel. okay? This step that I just wrote is not strictly not necessary, right? But you do have to cancel out that 2 somehow, right? So if you see that all of your factors have a 2 in them, or all of your terms have a factor of 2 in them, then great. If you don't see that, then you have to factor out the 2 from the numerator, and then you can cancel out the 2's, and then we're kind of good to go there. All right. So now this is simplified, but it's not rational. It's not rationalized because I have a root 2 in the denominator. So similar to A, I'm going to do this trick where I'm going to multiply by the number 1. But what I'm going to do is I'm going to write the number 1 in kind of a funky way. I'm going to write the number 1 as root 2 over root 2. And this is not going to change my quantity, right? It's going to this number is going to be just as large as it is now, okay? Because I'm not changing anything. I'm just changing the way it looks, all right? So multiplying fractions, I just multiply across. So in the denominator, I've got 4 root 2 times root 2. And what's going to happen is the root 2's are going to go away, and I'm left with just 4 times 2. Because root 2 times root 2 is root 2 squared. The squared and the square root go away, and you're left with just 2. So it's 4 times 2. I'll write it. I'll write 4 times 2, and we'll clean it up in the next step. In the numerator, that root 2 is going to be applied to both terms, okay? The parentheses kind of go away because the 2 goes away. But then it's almost like the parentheses come back because that root 2 is going to get distributed to both terms, okay? So root 2 times 1 is root 2. And root 2 times root 2, again, for the same exact reason in the denominator, is just 2. Okay. Now, in the numerator, it's kind of a mathematical convention when you have an expression like this to do the rational part first. So I'm just going to flip the order and make this 2 plus root 2. So again, in general, that's how you would write that. So I would encourage you to write that as 2 plus root 2. And then the denominator is 4 times 2, which is 8. And again, just like A, I have a root in my numerator, and I don't care because that's fine. In fact, in this question, it's necessary because you don't want the root in the denominator, which means it kind of has to be in the numerator, or it's like some other value, or it's a wrong answer, right? So B, final answer is 2 plus root 2 over 8. And I guess you could express that. I guess you could break that up into 2 different fractions, but I think I'd probably prefer it like that. So that's gonna be my final answer for B. Okay, C. Get rid of this extra stuff here. So for C. So for C, we've got a couple things going on with C. First of all, these square roots can all be simplified. I don't want a square root in the denominator, and one of them has a negative underneath it. So when you have a negative underneath a square root, you want to express that using I notation. You don't just want to leave the negative underneath the square root, right? So if it's an imaginary number, like use I. Don't just leave the negative underneath the square root and like walk away. Like you gotta just indicate that it's imaginary using an I. So again, a couple different ways you can kind of start this problem, but the way that we've done A and B, and the way that I'm also going to do C, is the first thing I want to do is I'm going to simplify each square root. So the numerator is the square root of 36. Well, that's actually kind of nice because that's a nice round number. That's just 6. So you don't have to sort of worry about, oh, the largest square number that goes into 36 is 36, right? It is itself. So because of that, it simplifies rather nicely to just 6. And then for the denominator, I've got the square root of negative 25. Now, in an earlier problem, I sort of took the long way, and I sort of showed you. This was 11D when I did this. I kind of took the long route, and I kind of showed you how this simplifies. I'm not going to do that again. I'm just going to take the quicker route. So what you have here, so if you temporarily just ignore the negative and just focus on the 25, well, the square root of 25 is 5. So the the number, I guess, the number part of the number simplifies nicely as just 5. But then you've got this negative, right? So what's left underneath the square root right now is the square root of -1, right? If I sort of like factor out the 25, I get 5 as the square root, but then I've still got a square root of -1, and the square root of -1 by definition is I, right? So that's where that I comes in because of the negative underneath the square root. So this is looking better. This is looking promising. However, just like with A and B, where we, when I say we, I mean mathematicians, and that includes you, we don't like roots in our denominator. Well, we also don't like the imaginary unit to be in the denominator, right? We want our denominator to be like clean, and there's reasons for that, but I'm not going to go into them right now. If you're curious, see me in person. But for reasons that I'd be happy to explain, we want our denominator to be clean. So we don't want roots and we don't want the imaginary unit. So we want to get rid of that. Well, we're going to use our same trick that we used for A and B, and we're going to multiply by the number 1, which we're allowed to do. And we're going to express the number 1 as I over I, which is 1. Okay, that is 1. So we're allowed to do it because it doesn't change anything. It's just going to make our answer look different. So when you multiply fractions, you just multiply across. So the numerator, well, that's pretty easy. 6 times I is 6i. Okay. And then the denominator is 5i times I, which is 5i squared. All right, well, on first glance, it looks like we failed because, well, we didn't get rid of I in the denominator, except, again, I've encouraged you to try to remember this. I squared is -1 because I is the square root of -1. So you square both sides, you get I squared equals -1, which means this is really 6i over 5 times -1. Well, 5 times -1 is just -5. Right, so our denominator becomes -5, okay? And then we're like 99% done. When you have a situation like this where you have the numerator and denominator are different signs, where like one of them is positive and one of them is negative, I would encourage you, pull the negative out front, right? Don't leave the negative in the fraction, just make the whole fraction negative. Okay, because this is true. If the top and the bottom, if the numerator and denominator are one's positive and one's negative, it doesn't matter which one's which because that's actually equivalent. Just pull the negative out, make the whole thing negative. So our answer is -6i over 5. That's our final answer. And these are all of our final answers for question 13.